Okay, so we're in week 4 right now. This is going to be chapter 2 of SAT content. Take a look at your syllabus. You'll see that your homework for this week is to complete and read the strategy sample questions. Page 7 to 8 are the questions, and 16 to 18 are the actual answers. Complete the chapter 2 practice quiz. Check your answers, please. And then finally, the practice section you'll see also with an answer key. So today we're going to take a look at chapter 2. Let's begin. First, we're going to start with our first section, just solving general equations. Okay, solving general equations. So first of all, we have to discuss an equation of the first degree is called linear. Again, it is linear when it's some variable to the first degree. So if you have like 2x plus 4 equals 7, that is linear because x is really to the first degree. But if this were 2x squared plus 4 equals 7, now this is quadratic. Okay, again, linear versus quadratic. So what we're going to study right now are just standard linear equations. So generally speaking, if you want to solve a linear equation, you need to do the opposite of what has been done to it. So let's look at our first example. Our first example here, we can see that it says 2/3 x is equal to -8. So I have to say to myself, what is being done to x? Well, currently x is being multiplied by 2/3. And a lot of people say, all right, well, multiplying by 2/3, so I need to divide by 2/3 on both sides. So again, if I had 2/3 x equal to -8, and a lot of people say, all right, as we say, let's divide by 2/3. Divide by 2/3 on both sides, but that's a little bit messy. And many of you know that when you divide by a fraction, all you should know this by now, but some people not recall it right away. But think about when you divide by a fraction, it's really multiplying by the reciprocal. So instead of dividing by 2/3 on each side, what I recommend you do, whenever you have an example with a fractional coefficient, you multiply by the reciprocal of that fraction. Let's correct that. You multiply both sides by the reciprocal of that fraction, and then go ahead and solve. So we'll see that our 3's will cancel, our 2's will cancel. We're left with an x there. On the right-hand side, we're going to have -8 times 3/2. Well, either you can multiply the -8 and the 3 and then divide by 2, or I could reduce initially. I'm going to choose to reduce. I'm going to make this -4, make that a 1, and then end up with -12. So in this case, x is -12. And if you go ahead and check that, you can try. Say, all right, well, 2/3 of -12, what is that value? Well, 2/3 of -12 happens to be -8. So this does check out with our first equation that was given. So again, think about doing the inverse operation of what is being done already. Let's take a look at a second example here. For the second example, where we have parentheses, there are several ways you can do this problem. Okay, first you could start by moving stuff over and dividing by the 3. What I recommend you do, though, is look and isolate. See that there's a b here and a b here. Those are going to become like terms. So let's go ahead and distribute this 3 before we actually begin. So this is an example where you have to use the distributive law before you can actually solve for the variable. So we end up getting 3b plus 6 plus 2b equal 21. And now at this point, we just solve like any other equation. Let's combine our like terms. This is going to become 5b, which is coming from the 3b and the 2b, yielding 5b, plus the 6 still, equals 21. Subtract 6 from both sides. Again, do this in your head. You don't have to write this down. You get 5b is equal to 15. Divide by 5. I already went to the answer. And you get 3 as your answer for the value of b. Okay, again here, notice, you don't have to show all these steps. So in this case, you don't have to show this division by 5 or this subtraction of 6. If you want to go straight from this line, straight to this line, and then to the answer, I encourage you to do that. Do a lot of the mental math, again, mentally, in your head. You do not need to show those steps if you don't have to at this point. Let's take a look at a third one. And for those of you who remember, these are just rational expressions. And what we talked about in rational expressions is simply to get an LCD of everything and then solve what results. So let's take a look. I see that this is really a denominator of 3, a denominator of 4. Well, this is really a denominator of 1. So my common denominator already is just a product of whatever I have in the bottom. A simple way to do it. So for this case, I would say 12. Well, then I have to say to myself, all right, well, I've got m over 3 minus m over 4 equal to 2 over 1. That's what I have right now. And let's see, I want to get a 12 in the bottom. So I have to say to myself, what number in the beginning here do I have to multiply to get 12? Well, what number times 3 gives you 12? It's just a 4. So you put a 4 on top and the bottom.
AP teachers will be near. Ms. Joyner. Thank you.
Next, we have the second part of this problem to multiply. We see that there's a 4 in the denominator. So we want to make that a 12. We multiply by 3 in the top and the bottom. So we still have a 12 there. And now the last part that some people do forget about, on the right-hand side I need a 12. And I only have a 1. So only 1 times 12 will give me 12. So I have to multiply by 12 over 12. Now what's going to result from this is the following. 4m over 12 minus 3m over 12 equals 24 over 12. This is very interesting to look at because what you notice is everything is being divided by 12. So I could simply just cross them out. Again, none of the 12s have any effect on the problem anymore because everything is being divided by it. Another way to think about it is this. You've got all the 12s there. We'll multiply this side by 12 and multiply this side by 12. If you do one thing to one side, you have to do it to the other. Well, this 12 reduces, and then this 12 has to get distributed on the left-hand side. So this actually cancels with both of these 12s, which in the end still yields 4m minus 3m equal to 24. So to summarize for this kind of a problem, you want to get a least common denominator, which is great, but then after that, just solve what's left in your numerators. 4m minus 3m is 1m equaling 24, which is our solution for that problem. Okay, let's take a look at the next one. A very common example on the SAT, you have to solve a proportion. A proportion is very simple to solve if you have one set up like this especially. Just simply cross multiply. So let's start by multiplying in this direction and then multiply these two. So the first circle, which is x times 5, is just going to be x times 5. The second one is going to be x plus 4 times 3. I'll use parentheses to make it more clear. So again, what am I doing? I'm multiplying the x times the 5. That's on my left-hand side. Doesn't matter which side. And then the 3 times the quantity x plus 4. I'm saying the quantity to remind you that you need to put parentheses around your x plus 4. Therefore, forcing you to remember to use the distributive property here. X times 5 is simply 5x. That's the easy part. But on the right-hand side, now we have 3x plus 12. If we go on to solve this, we can say, all right, well, I'm subtracting 3x, subtract 3x. I end up getting, I'll move to the right over here now, I end up getting 5x minus 3x is 2x. On the right-hand side, those cancel. 2x equals 12. Divide by 2, divide by 2, x is equal to 6. We have to always make sure we go back and check for denominator restrictions, though. So first of all, we have to say, well, is this number 6 going to cause a 0 in my denominator or cause an undefined problem? And clearly, the 6 would not even be put into the denominator. If you were to check this problem, it would go in the numerator. And we can check that. We'll get 6 over 3, that's 2. We get 6 plus 4, which is 10 over 5, which is also 2. So this would become a 2. That would become a 2. 2 is equal to 2. We know that is correct. Okay, a simple way to check that. What you really want to check for in the SAT, though, are checking for denominator problems. So if an answer causes the denominator to become 0, you have to reject that answer as your solution. Okay, using a root of an equation to answer a question. Well, this is a very common question on the SAT. You do all this work, it says, figure out the value of y minus 2. And a lot of students do a great job here. They start and they say, all right, I'm going to add 2, I'm going to add 2. I see that I get 3y is equal to 6. I'm going to divide by 2, divide by 3, divide by 3. Again, sorry, I gave you the answer. Divide by 3, divide by 3, we get y equals 2. And a lot of people, you know what they choose? They choose 2 as their answer. But take a look at this problem here. When I look more carefully, it says, what is the value of y minus 2? So I need to take this and plug it in there. Well, what's the value of y, which is 2, minus another 2? 2 minus 2 is just 0. So your actual answer is this value 0 right here. Because the problem does not ask you for the value of y. Yet the problem asks you for the value of y minus 2. Y minus 2. Okay, let's take a look at the next example now. Second section here. So what if we have an equation with more than one variable? And by more than one variable, really I'm talking about different variables. So x can appear twice. That's not more than one variable. But in these examples we're going to see we have x and we have y in them. Okay, and some of these can be answered very simply. I'm going to show you some tricks along the way. And these are the kind of things you want to pick up on while you're taking the exam. So this problem starts by saying 4x and 4y together come out to be 12. But then it says, what is the value of 2x plus 2y? A lot of students try to say, all right, let me solve for x and solve for y and substitute and do a lot of work. When in reality, you can pick up on some stuff. So first, notice here, x and y are both separated by a plus sign. Here, they're also separated by a plus sign, which helps us right away to see the similarities. In addition to that, many of you probably noticed already that 4x plus 4y is just double 2x plus 2y. So if you start with 4x plus 4y, and you know that that's equal to 12, if you want to know what 2x plus 2y is, just halve this and halve this side. And what you end up getting is 2x plus 2y, and you're going to just get 6. Again, because this 4 over this 2 is simply 2, and this 4 over 2 is simply 2. Remembering that when we divide by a monomial, one term, when we divide by a monomial into a binomial, it must divide into both terms. And then 12 over 2 is, as we can see, 6. Okay, so again, in this problem, it looks very complicated at first, but what you can notice is that it actually reduces simply. Let's take a look at this next example, which is one of the most common examples in the SAT, when they ask you to solve for a variable in terms of another. So, before we even begin this problem, we have to discuss what this means. In terms of, here's what you want to write down for this. It will be in the answer. So they're saying, solve for x with a y and a z in the answer. So you need to get x equals something that has a y and a z in the answer, or at least a y or a z for now. It doesn't have to have both. But x is going to equal something with y and or z in the answer. So let's go back and take a look. So again, I'm solving for x. What is x? So let's look at our equation. We have 2x minus z equal y. If I want to get x by itself, I need to perform my operations as directed earlier. So I see that z is being subtracted, so I'm going to start by adding z to both sides. Well, you might ask yourself, what is y plus z? Those aren't numbers, I can't add them. So you simply write them as y plus z. So your answer from this, you end up, the z's drop off obviously. We end up getting 2x equals y plus z. Well, the problem doesn't say find y and z, find 2x, it says find x. So in this case now we have to still divide by 2. And you're going to notice that we get x, the 2's drop off, x equals simply y plus z over 2. Okay, you know what? Let's say you're taking the test, let me fix this 2 so we can see it's not a z there. Say you're taking the test and this doesn't come up as a choice though. Well, there are other ways to rewrite this. I could write this as x equals y over 2 plus z over 2. I write my 2's consistently. Okay, that's one way of writing it. So this could be right, or we could write that. Or I could write this as a decimal. I could write it as x equals 0.5y plus 0.5z. Because again, dividing by 2 is the same as a 0.5 in the front. Dividing by 2 is 1/2. 0.5 is really 1/2. Or I could write this as x equals 1/2, since they're both at halves there, y plus z with parentheses around it. Because it's really like I'm factoring out the 1/2. There are many other ways I can write this. I can write it as or, let's see, x could equal 0.5 parentheses y plus z. Or I could write this as, let's see, or is that the last way? Let's see if there's any other way to write this. 0.5 factored out, 1/2 factored out. Yeah, that's pretty much it. Okay, so we're going to be looking at those possible answers. So take a look. You've got not 1, not 2, not 3, not 4, but 5 different ways to show the exact same answer. And that's one of the toughest parts about the SAT. You might get this answer right here, the first one that we got in the beginning, but it might not appear as a choice. So you need to manipulate and change your answer so that it does appear as a choice. So you have to say to yourself, well, what are the other representations of quantity y plus z over 2? Well, I can see it as y over 2 plus z over 2. I can see it as a half of y and a half of z. I can write it as a half of the quantity y plus z. I can write it as a half, as a decimal, quantity y plus z. Again, any of these ways are acceptable. It's up to you to decide what you need for the problem. All right. Let's take a look at some examples with polynomials. So if we're looking at some operations, adding and subtracting. Again, adding, you're just combining like terms. That's it. And it's the same thing for subtraction. And if you had me this year, you'll remember that as well. We talk about subtraction being defined as adding the opposite. So these are like terms. Together they become 3x squared. These are like terms. Together they become simply 2x. And finally, 7 and negative 9 together become negative 2. There's your answer. This should be a guarantee, automatic points on this on the SAT. Next one. Instead of adding, instead of subtracting, I would write this as adding and put all my opposite signs here. Because if you remember, we talked about addition and subtraction being really the same operation. Subtraction is really adding the negative value. So now I can look and say to myself, okay, now where are my like terms? I've got 7x's and a negative 5x. That's simply going to give me 2x's. I've then got negative 3y and negative y being negative 4y. And this really helps with mistakes along the way, because I can see they're both negative, still yielding a negative. I have negative 9z and 4z, yielding negative 5z. Okay, so go ahead and take a look at these examples, make sure they make sense. Multiplying and dividing. Let's take a look at multiplying and dividing. First, if we're multiplying different things that are not binomials, if they're simply monomials, okay, we have to use our exponent rules here. So first we see that we have a negative 2 times negative 4 giving me a negative 8. My next rule, I know that a squared times a cubed is simply a to the 5th, because I remember that my rule is a to the b times a to the c is really a to the b plus c. So if I ever multiply two things with the same base, I can simply add their exponents. And then finally, the last part, I'll look at my b values. I've got a b here, which is really b to the 1. I've got a b squared, yielding b to the 3rd. And there's my answer. Let's take a look at the next one. Here we have division. Whenever you have division, think about subtraction instead. First start, let's reduce. 14 over 21 is really 2/3. How do I know that? I just divided both of them by 7. Reduce by a factor of 7 first. So my answer will have a 2/3 for sure. Next, x to the 5th and x to the 2nd. Well, this is really like having 5x's up top. This is really like having 2x's down below. So if I think about it, I'm really going to have 2x's and 2x's cancel. I'm left with simply 3x's, or x to the 3rd. Well, the other way you can do that, as we said a minute ago, is by using our exponent rules. This is really x to the 5th and x to the 2nd. 5 minus 2 is what gives me this 3 here. And then finally, y squared over y squared, they just cancel. Again, if you have the same thing over itself, it reduces at 1. So my final answer can be written as just simply 2/3, and I can write the x cubed by itself like that, or I can write it as 2x cubed over 3. That's another way to write it. Okay, either one of those ways are fine. Again, go back to your exponent rules. Look at more complicated stuff than that, please. Look at some practice examples, please. All right, if we're multiplying a polynomial by a monomial, just use your distributive laws. Let's go ahead and do that. Distribute, please, to each of these three terms. 5x times 3x is 15x squared. Again, 5 by 3 is 15. X times x is x squared. Next, 5x times negative y. Consider the negative and just put it right here. And then just put 5x, and you're multiplying it by y, thus 5xy. That's this middle part right here. Then I need to do 5x times 2. Well, 5 times 2 is just 10, and then tack on the x. And there's my final value for that problem. Okay. All right. To divide a polynomial by a monomial, divide each term into the numerator, just as we said earlier. So divide this 3 into both. Think of this as 6x over 3 plus 15 over 3. It's like the reverse of adding and subtracting fractions. Right now you have a common denominator, so you could add these together. But I'm splitting it up. I'm splitting it from here to there. And now just simply reduce. 6 over 3 is 2, so that's 2x. 15 over 3 is 5. 2x plus 5. So a monomial gets divided into both terms of the binomial, or of whatever the polynomial happens to be. All right, multiplying, you can use FOIL or you can use box method. Either way, whatever you would like to do. FOILing, first is 2x squared, outer is minus 10x, inner is plus 1x, and then finally last is minus 5. Combining your middle terms, you get 2x squared minus 9x minus 5. Okay, please, if you can do this stuff in your head, do it in your head. If you want to try box method, 2x and the 1 goes up top, x minus 5 goes on the side. It doesn't matter which one goes where, as long as you're consistent. 2x times x is 2x squared. This is going to be, let me show how we do this. We do the 2x times the x to get the 2x squared. Then we do the 1 times the x to get the x by itself. After that, we do the 2x squared times the negative 5, yielding negative 10x. Finally, we take the 1 times the negative 5, yielding negative 5. Add up what you got here. You get 2x squared. These two reduce to negative 9x minus 5. Exact same answer as we had before. Okay? Either way, either or. Pick to choose which one you would like to do. Some quick rules. Difference of two squares. Please make sure you memorize these. Whenever these happen to be perfect squares, each term, and there's a difference in the middle or a subtraction sign, hence difference, we can simply say that we can know our rule that x squared minus 9 is x plus 3, x minus 3. Where pretty much I take the square root of this and take the square root of this. And go ahead and FOIL it back out to check. If you FOIL this back out, you're going to have what x squared plus, or sorry, let's say minus if we do it in the correct order. X squared minus 3x plus 3x minus 9. The middle terms cancel. You're left with x squared minus 9. Okay, which is exactly what we started with, x squared minus 9. So difference of two squares, everyone here should be familiar with that by now because we've done it so much in class. All right, combining algebraic fractions as a symbol or as a single fraction. Common denominator, common denominator, common denominator. W over 2 minus W over 3. Think to yourself, what is the common denominator here? Oh, well, clearly I can see that 2 times 3 is 6, so 6 might be my denominator. Sorry, water break. Now, if I want to consider this, I want to say to myself, how do I get a 6 in the first denominator? Well, I need a 3 here. How do I get it over here? I need a 2. But I can't just multiply by 3 in the denominator. I have to multiply by 3 over 3, hence 1, or not changing the value. Here I have to multiply by 2 over 2, or 1, thus not changing the value. And now what I'll notice is this case, again, this is an expression. We're just simplifying. We're not solving an equation here. I'm left with 3w over 6 minus 2w over 6. Well, common denominator means I can make it as one denominator, and then I have 3w minus the 2w, which is just 1w, or w over 6. Which, by the way, can also be written as 1/6 w. Again, keep that in mind. There's really an invisible 1 here. So you can write that as 1/6 w, where the w is a term by itself. Okay, not a term by itself, sorry, is a factor by itself. 1/6 is one factor, w is the other factor. All right. Let us take a quick look at this next example because this involves algebraic fractions. So, this problem tells us that h is defined as y over the quantity x minus y. And it says, what is h plus 1 in terms of x and y? And in this kind of a problem, it'll be a multiple choice. So let's go ahead and take a look. Let's dig into it. So I want to know what h plus 1 is. So I'm going to sub in for h right away. I'm going to sub in y over x minus y. And I have to add 1 to it. But I can't add these together because I don't have a common denominator. This problem is a little bit difficult because a lot of people forget it's really 1 over 1. And now I can see if I want a common denominator, just multiply this by x minus y over x minus y. Doing this, I'm going to see that my denominator becomes simply x minus y in both cases. So I can write it as one denominator. Whereas my numerator is y plus x minus y. Well, take a look. I've got a positive y here. I've got a negative y here. The parentheses can pretty much be dropped because there's a plus sign here. And we know that addition is associative. It does not matter what order I add them together. So I can drop the addition sign there. So here in this case, or not, it's associative, I can group it either way. Sorry, I can group it either way. Commutative would not matter which order. But in this case, the grouping does not have any effect on the problem. So this y cancels this y, and I'm left with x over x minus y. Okay, again, multiple choice. Good problem for multiple choice. All right, factoring, everybody's best friend. First, you have to start with the GCF. Before you do anything else, GCF, 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 every single time. So in this problem, what I'm going to notice here is that 24 and 16 are both multiples of 8. So I can take an 8 out right away. Okay, I can take an 8 out. I also notice that there's at least one x in both terms. I want to look for the greatest possible amounts of x's. There's 3 of them here, sure, but there's only 1 here. So I can only take out 1 of each. Now, the easiest way to remember what's left over, in your mind, divide by your GCF. You end up here getting just 24 over 8, which is 3. X cubed over x is x squared from our rules earlier. Next, I'm going to get 16x over 8x. The x's cancel, and 16 over 8 is just 2. I carry the plus sign over from here into the middle to remind myself. And go ahead and check. FOIL, distribute back out, and what you're going to notice here is that you do get back to 24x cubed plus 16x. All right. Using factoring to isolate variables. So we want to solve for x in terms of the other variables, but clearly I can see that x is over here and x is over here. So to get x by itself, I'm probably going to have to either combine like terms or factor it out. Now, I can't combine like terms really because I don't have any numerical coefficients. I have all variable coefficients. So in this case, my recommendation to you, let's start, ax minus c equals bx plus d. If you need to get x by itself or solve for x, get them over to the same side. So start by adding c to both sides. I'm going to be left with on the left side ax, because these c's cancel. Now I have bx plus d plus c, which is fine. We're good to go. Now I'm going to move this up. I'm going to rewrite it, sorry. Now at this point, let's subtract bx, because bx is currently being added. Again, there's really an imaginary plus sign in front of here. So let's subtract it. Subtract bx, subtract bx. You get ax minus bx, these drop off, equals d plus c. But you still need to get x by itself. Well, go ahead and factor an x out now. If you factor x out, you're left with a minus b in parentheses, and you have a d plus c here. Again, if I factor an x out, this x comes out front. Along with this x, there's no x's left behind. And now I want to solve for x. Well, x is currently multiplying the quantity a minus b, because there's really a multiplication sign right there. Again, there's a multiplication sign between the x and the actual quantity a minus b. So since there's a multiplication, we do the inverse of multiplication, which is division. So divide by the quantity a minus b, divide by the quantity a minus b. Now you can say your final answer. X is equal to d plus c over a minus b. Okay? All right. Let's take a look at factoring trinomials. We've done all these steps before, so I'm going to quickly go through what you need to do here. Remember, on the SAT, the factoring questions are very simple. They're not going to be tough problems where you need really AC method used. So think to yourself, what are the factors of negative 14 that add up to negative 5? So you want things that multiply to give you negative 14 and that sum up to negative 5. So start by listing the factors of negative 14. Negative 7 and 2, 7 and negative 2, negative 14 and 1, 14 and negative 1. That's it. And out of those 4 choices, which adds up to negative 5? Many of you noticed right away, it was the first option. So I break this up and I factor. And many of you are great at this by now, and I assume that we all are here. So it's x minus 7 and x plus 2. Okay? Again, this problem is just asking to factor. If it said find the roots, we can make our t-chart, set them each equal to 0, and get 7 and negative 2. But it's not asking for the roots or the x-intercepts here. It's just saying to factor. All right? Again, the difference of 2 squares, we already looked at this one. If you have 2 squares and they're perfect squares, break them up as their squares. As you see here, put a plus and put a minus. That's one of our rules that has got to be memorized. All right, next one, factoring completely. I'm going quickly here because we just did this in class, so it should be fresh in everyone's mind. Here, what are the numbers here? Well, I see that there's a t in every term right away, and it's cubed. It's not squared anymore, so I can't just factor. But if there's a t in everything, I have a GCF. Okay, so please start by taking out the t. Once you take out the t, then we need to factor what remains. Well, what are the factors of 9? The factors of 9 are 3 and 3, negative 3 and negative 3, 9 and 1, negative 9 and negative 1. Well, which of the following here multiply to give you 9 and add up to negative 6? And you'll notice that these are the only ones that add up to negative 6. So it's x minus, not x, t. T minus 3, t minus 3. Which can be written as t, parentheses, t minus 3 quantity squared. Because I really have a t minus 3 and a t minus 3. So keep that in mind. Any of those answers are acceptable, especially if it's multiple choice. Again, please, if this is too fast, pause the video, slow down, work them out on your own, and then listen again. Okay, that's why you have the option of listening to this recording. It helps a lot here. You can pause whenever you would like. All right, so we want to simplify an algebraic fraction here. Let's factor each of them and see what cancels out. So we're simplifying, we're simplifying, we're simplifying. So please start by factoring. In the numerator, everybody should see a 2. You're left with b minus a. Denominator, you've got difference of 2 squares, so it's a plus b and a minus b. So at first, a lot of people get stuck here. And the reason they get stuck is because they don't see the same factor canceling. And I agree with you, I don't either. But if you remember, we talked about this year in Algebra 2. Whenever you see a quantity like this, right here, b minus a over a minus b, that actually does reduce, but it leaves behind a negative 1. And the simple proof is the following. Look at 2 minus 4 over 4 minus 2. Well, 2 minus 4 is negative 2. 4 minus 2 is positive 2. That reduces to just negative 1. So whenever you have numbers that you're subtracting and they're switched in the top and the bottom factors, just cancel them and leave behind a negative 1, not a positive 1. So you're left with 2 over a plus b times negative 1, really. That's what these cancel and reduce to. Well, you might just say, sure, Mr. Howell, that's just negative 2 over a plus b. Absolutely. Move the negative 1 into the numerator, write it as negative 2. Let's take a look at some quadratic functions and equations here. All right. For example, for what values of x is this factored quantity equal to 0? Well, it's just saying find the roots, find the x-intercepts. Well, what could cause this factor to equal 0? Or what could cause this factor to equal 0? So what do? We make a t-chart. X minus 1, x plus 3 equal to 0. Well, if one of the factors is 0, then the whole thing is 0. So we have to try by setting each of them individually equal to 0, which many of you know from class by now. You just simply get the opposite of the roots, the opposite of the factors, okay? The roots are the opposite of the factors here. Again, this only works when you have a 1 here and a 1 here. The minute those are not 1s there, if that's a 2 or a 3 or 4, you need to go through the problem and actually solve it. You need to actually solve it. All right, so the next problem. I'm not going to go through all the steps that are written down, just read through them. Whenever you're solving a quadratic, move everything to one side. That's my key. My suggestion again, move it all over, get a 0 on one side. So here, if I move this 2x over, again, I've got x squared equals negative 2x. How would I move a negative 2x over? Well, add it. Okay, add it. And it looks at first like, all right, well, 2 can't combine with the x squared, fine. So this just becomes x squared plus 2x. Just combine these two like that. Well, that equals 0 because those drop off. And now what you notice, which a lot of students forget about, GCF. Go back. X parentheses x plus 2 equal to 0. Set each factor equal to 0 individually and solve. Well, x equals 0 is solved already. We're done with that. What does this solve to be? X equals negative 2. So I have two solutions here. One is 0, one is negative 2. Next example, I've got a trinomial here. The reason I know I have a trinomial is simply because I see that I have 3 terms, all of which are not like terms. So move the 10 over by subtracting 10, please. You end up with 0 over here because 10 minus 10 is 0. X squared plus 3x minus 10. Please factor. Here, what number is multiplied to negative 10? Well, multiplied to negative 10 is negative 5 and 2, or 5 and negative 2, negative 10 and 1, or 10 and negative 1. You choose. Which of those adds up to 3? The only one that adds up to 3 is this row here. So this becomes x plus 5, x minus 2. But again, remember, I'm solving for x. I'm solving for x. So I make my t-chart. X plus 5 could be 0, or x minus 2 could be 0. So x could be positive 2, or x could be negative 5. Again, do this in your head if you can. Please don't waste your time writing it down. The next example is very interesting. They give you one of the roots, and you have to remember what a root means. A root means the x-intercept, or the x value it can take on. So if 4 is a root, just plug it in for x to find w. Again, you're solving for w. Well, you can't solve for w unless you know these x values. But you are told that x is 4, because x equals 4 is really the root. So here I put in a 4 squared, minus 4 minus w equals 0, 16 minus 4 minus w equals 0, 12 minus w equals 0, or w equals 12. So whenever you're given a root or an x-intercept or a 0 of the function, you can start by plugging it in for x to solve for what remains. Let's look at systems now. All right, systems. We did a lot with this year. Think back to concepts 25 through 29. We looked at substitution, we looked at elimination. Now, there are certain circumstances where one is easier than the other. For this circumstance, the problem here asks us to solve for the value of y. So what I would do is try to get rid of x, really. I want to get rid of my x. So in this case, I can do this several ways. I see that y is already solved for. So a lot of students start by taking this value and plugging it in for y, which is fine. You get x plus 2x minus 3 equals 18. Combine like terms, you get 3x minus 3 equals 18. 3x equals 21, so x is equal to 7. Well, that's not the problem asked, though. The problem asked for y. Well, you can go and plug this back in now. Plug in the 7, back up there for x. You're going to get y equals 2 by 7 minus 3. 14 minus 3 is 11. So you can do it that way, and that's fine. Solve for y, you get y equals 11. But what I really encourage you to do is to think about what you're actually being asked. The problem asks for y, so try and eliminate x. So what I would do actually here is this. I would solve for x here. I would subtract y. I would get x equals 18 minus y. Then I would take 18 minus y and plug in it up there, so which would yield y equals 2, parentheses, 18 minus y, minus 3. And now when you solve this equation, you're solving for y. It really doesn't matter either way. One might be faster than the other, but that's your judgment to use there. Oops, 2 times 18, let's actually distribute that. 36 minus 2y minus 3. I'm going to get y equals, and I'll combine like terms. These are clearly like terms. That's 33 minus 2y. I'm going to add 2y. I'm going to add 2y. It's going to become 3y equals 33, and thus y equals 11. Same exact answer as before. Okay, so what have we done here? We've done substitution method. Substitution method. Okay? Let's look at the second one. This says find the value of x. But to find the value of x, I really need to get rid of y. Because here, I've got x and I've got y. So let's solve for y over here, actually, and then plug it in. So let's combine like terms. Let's add 5 and add 5. I'm going to end up getting 8 minus y over here equals y. I'm going to add y and add y. I'm going to get 2y equals 8. Therefore, y equals 4. The problem didn't say find y. It said find x. So the substitution method tells me, take that 4, plug it in up there. Okay, plug in the 4 up there, and we can actually go ahead and solve this. 2x minus 3 by 4 equals 6. 3 by 4 is 12. I'm going to add 12 to both sides, giving me 2x equals 18, and thus x equals 9. Okay, so substitution method can work in several different ways. Again, a lot of these are basic problems. You need to look at the more example or more difficult problems in the other examples in the practice sections that are solved. Please make sure you're doing that. Here we can see that clearly we're going to use elimination method. And the reason I can tell you right away is because I've got it all lined up. X, Y number, X, Y number. And it turns out that the y's happen to be opposite each other. So simply add the equations together. So write them in row form. Okay, writing them in row form, I can just add straight down. X plus x is 2x. Negative 2y and positive 2y is 0. and this gives me 16 on the right. So 2x is equal to 16 really, thus x equals 8. And a lot of people see this problem and like, wow, 2 equations, 2 unknowns, I gotta find x. Look at that, 15 seconds, you're done with that problem. All right, next example. If 2a is equal to b plus 7 and 5a is equal to 2b plus 15, what is the value of a? What is the value of a? All right, looking at this problem, my first thought is this. I need to get rid of b. So theoretically, I could use substitution method here. But personally, I would not use substitution. I would use elimination. I would start by listing. So I got 2a equals b plus 7, and 5a is equal to 2b plus 15. Now, you might want to say, well, what if I just add down again? Try it. You get 7a plus equals 3b plus 22. Does not really help me here. So what I need to consider now is to think about the fact that I need to get the b's to drop off. So if I have a 2b here, I want to have a negative 2b here. So if I multiply this to give that a negative 2b, I have to multiply the whole equation by negative 2 here. So this ends up, if I multiply by negative 2, I get negative 4a equals negative 2b minus 14, remembering that you have to distribute the negative 2 to both terms. And now I can see that simply the 2b's are going to now cancel. 5a and negative 4a is 1a. The 2b's cancel. 15 minus 14 is 1. A is equal to 1. Again, notice about 3 steps there. You're done with the whole problem. Practice, practice, practice. This will get a lot easier. That's why it's second nature to me. All right. Solving other types of equations. Okay, this is a good one. 2 variables in terms of other variables. So, for this example, let's start by identifying what we're looking for. We're looking for r. Well, I have r. It's right here. I could solve for r, but it says find r in terms of t. This r, if I solve for it, let's go ahead and solve right away. Solve for r. Divide by 2, divide by 2. I get r is equal to s over 2. Okay, s over 2. That's great. I got r. But it says, what is r in terms of t? Which means that t must be in the answer. It must be in the answer. All right, so, oh no, this looks really confusing now. But I see that I have a second equation here, and that has a t in it. So if I see that there's an s in there, and there's a t in there, I can then solve for s over here, and say, all right, well, you know what? 2r is equal to s. Well, that goes back to my original statement right here, actually. If I take this 2 and move it on up, I get the same statement. So what we could have done in the beginning would just be to substitute in for s, right there. So we take this equation now, this 24t equals 3s, write it as 24t equals not 3s, but instead of putting an s in there, I replace the s with 2r. So I put the 2r over here. And now I can solve for r in terms of t. 24t equals 6r over 6 divided by 6. I get r equals 4t. Okay, again, r is equal to 4 times t. We have solved for r. We have solved for r in terms of t, not in terms of s. Again, this is not our final answer. That was an intermediate step that didn't end up helping us. All right. Next example, I want to find out the value of a divided by c. Okay, a divided by c, which seems to be a little bit messy. But think about this. You have an a in both. You have a b in both terms here, and you have an a in one and a c in the other. So I'm clearly going to want to divide eventually, but I can't start dividing without altering this a little bit. So let's take a look. If I add 3 and I add 3, I'm going to get ab equals 15, and I'm going to get 2bc equals 5. All right, so far so good. That's not bad. So I want to say to myself, all right, I want to get a over c. What if I take one equation and divide it by the other? Well, that seems to work. Let's take a look. ab equals 15. Take that whole equation and divide it by 2bc equals 5. Weird, right? Isn't that weird the way this works? Well, let's take a look. B's drop off. 15 over 5 is just 3. So I'm left with a over 2c is equal to 3. But I want a over c. So this 2 is in the denominator. So I need to take this 2 and move it on up to the numerator. Okay, or remember, just multiply both sides by 2. multiply both sides by 2. The 2's cancel. You're left with A over C, and 3 times 2 is just 6. So the quantity A over C is equivalent to the number 6. All right, and finally the last section for today, algebraic inequalities. The examples you're going to see on the SAT are very, very straightforward for these. Okay, they're very straightforward. Where they come up are examples where they ask you for the greatest or least integer. So we have to talk about that. Let's discuss this first example. Think of it like an equation. That's my first suggestion always. So subtract 3 and subtract 3. We get negative 3x is greater than 6. Now, the only trick, or the only difference here, you'll notice the only difference is when you multiply or divide by a negative quantity. You have to reverse the direction of the inequality. So here now I want to solve. So I'm dividing by negative 3, divide by negative 3. I need to reverse this. Reverse this. So I get this, I have x, and this is going to be negative 2. So x is less than negative 2. How would you visualize that on a number line? Well, here's 0, here's negative 2. Everything to the left of negative 2 is all this region shaded in, and since it's just less than, it would be an open circle. Okay, that would be my solution set for that problem. Let's look at the next example now. Okay, we're almost done. So we've got 3x minus 2 equals, or is less than 10, and it says find the value of x. So again, as last time, add 2, add 2. 3x is less than 12. Divide by 3, divide by 3. X is less than 4. Boom, you're done. Okay, just keep that in mind. You're going to have to use this knowledge when you do these other problems. Let's look at the next example, really, because this is the one that the SAT will ask. What is the greatest integer value of x such that 1 minus 2x is greater than 6? Is greater than 6. What are the greatest integer value? So let's start by solving. First, I can move the 2x over and then move the 6 over, or I can move the 1 over. It doesn't matter. I'm going to start by subtracting 1, subtracting 1. I'm left with negative 2x, because the 1's cancel, is greater than 5. I need to divide by negative 2, which indicates that I have to flip a sign because I'm dividing by a negative. I get x, now instead of greater than, is less than, and 5 over negative 2 is negative 2.5. So my answer is really x is less than negative 2.5. So this is where your number line comes into play. So here's 0, here's negative 1, here's negative 2, here's negative 3, here's negative 4. Well, negative 2.5 is here, and everything less than that is over here. And this problem says, what is the greatest integer? Greatest. And you got to remember that in math, greatest means the number furthest to the right. So a lot of people think about like negative 4. Oh, negative 4, they think negative 4 is bigger than negative 3. That's not correct. The absolute value of negative 4 is greater than the absolute value of negative 3. But in this case, the greatest integer would be negative 3. Again, because my solution set are all the numbers negative 3, negative 4, negative 5, all my integers, those are part of my solution set. Well, which is the biggest? The biggest integer is negative 3. All right, and let's take a look finally at combined inequalities. Combined inequalities, think of it as two separate inequalities. So please break it up. Negative 2 less than or equal to 3x minus 7. Over here, think of it as 3x minus 7 less than or equal to 8. Okay? When you see this conjunction in the middle, okay, the conjunction, you want to think of the word and. You want to think of the word and. Now, let's solve these individually. Move the 7 over. I'm going to get add 7, add 7. I'm going to end up getting here just 5 less than or equal to 3x. Divide by 3. Okay, we get x is greater than or equal to 5/3. 5/3, we can think of it as 1.6 repeating also. On this side, let's add 7 and add 7. Get 15 and 3x. Divide by 3, I get x is less than or equal to 5. So, as a solution set, I want to think of it on a number line again. So, I know I'm going to range from 1.66666 all the way to 5. So I'm just going to go from 0, I'm going to put a 5 here, I'm going to put my 1.6 repeating here. Okay, everything, again, let's read these. X is, and I'm reading it from right to left, x is greater than or equal to, again, this says x is greater than or equal to 1.6 repeating. So one of my solutions looks like this. And I'm going to draw them above each other for a reason. One of my solutions, the one I underlined in green over there, is everything greater than or equal to, so I color in the circle because it's greater than or equal to. Whenever it's equal to there, we color it in. And it's greater than or equal to 1.6, so it's everything to the right. Okay? But the other solution says x is less than, and I'm going to read it from left to right this time, x is less than or equal to 5. So the other solution is everything from here backward. Well, you can't have more than one of these regions because we want a solution that has the word and here. So what we have to do is think about this. Where do they overlap? And clearly they overlap from 1.6 to 5. So in interval notation, which many of you know from this year, my solution set would be bracket 1.6 comma 5 bracket. Fine. But in set notation, which is what the SAT tends to use, I would write it as 1.6 less than or equal to x less than or equal to 5. So either one of those solutions are fine. All right, so that brings us to the end of this video. Brings us to the very end of it. Again, remember what you're supposed to be doing for week 4. Please complete pages 7 and 8. Check your answers on pages 16 to 18 of the strategy sample questions. Complete the chapter 2 quiz and then look at the solution. You'll see a solution up for this notes we just took. And then look at the practice section and please look at its solution as well. Hope you enjoyed the video. See you next week.